Okay, in today's lesson we're going to discuss transformations or transformations of functions. Alright, and basically what we're talking about with transformations is how we want to go about manipulating standard basic functions, or what we would call parent functions. Okay, so first I just want to give you a look at some of the parent functions. Alright, so one of the parent functions is f of x equals x. So this would be a graph of that parent function. Another parent function okay, this would be an example of the parent function f of x equals x squared. Another parent function we would have f of x equals absolute value of x. Getting still another parent function being f of x equals square root of x, and I'll give one more. Alright, and this is f of x equals x cubed, x to the third. Alright, so again, these are what we call our parent functions, and these actually aren't all the parent functions. There are others, okay, but for the sake of this lesson we'll just go with these 5. These are some of the more common ones. Okay, and when we're talking about transformation, basically we're just talking about how can we manipulate these various parent functions. And by manipulating I mean moving them, rotating them, stretching them, compressing them, things of that nature. Okay, so let's start by saying f of x equals x squared. Okay, or better yet, I might need to go ahead and clear the board for this. Okay, so let's look at f of x equals x squared, and then let's look at f of x equals x squared plus 1. Okay, so if we were making a table of values, x and y, let's say we have -2, -1, 0, 1, 2, and we'll do the same thing here. Alright, x and y, or by y I mean f of x, of course. Okay, so -2, -1, 0, 1, and 2. Okay, so for this function, when x is -2, f of x, or y, because remember y is f of x, so y is f of x. So if I plug in a -2 for x, -2 squared would give me a 4, so f of x or y would be 4. If I plugged in a -1, -1 squared would be just a 1. Okay, plug in a 0, 0. Plug in a positive 1, 1 squared would be 1. Plug in a positive 2, 2 squared would give me 4. So I have those points there. Now let's look at this one over here. If I have -2 okay, plugged in for my x, negative 2 squared, we said was 4, plus 1, now this becomes 5. Negative 1 squared is 1, plus 1, 2. 0 squared is 0, plus 1, 1. 1 squared is 1, plus 1, 2. 2 squared is 4, 4 plus 1, 5. Alright? So now, let's try to graph them. Alright, let's see here. Okay. Best as possible. Okay, try to keep it straight. So now my base graph, I'll just go ahead and plot it as it is. So 0, 0. I have a negative 1, 1. Positive 1, 1. Negative 2, up 1, 2, 3, 4. And a positive 2, up 4. Alright, so what I'm seeing is a graph that's looking something like that for this one, this function. Okay, so that's this graph you see here is f of x equals x squared. Now let's look at this one here. Okay, and I'll do it in a different color. So let's go with red. I have my negative 2, 5. Alright, at x is 0, y is 1. So at x is 0, y is 1. So there's a point. At negative 1, y is 2. So at negative 1, y is 2. At positive 1, y is 2. At negative 2, y is 5. And at positive 2, y is 5. Okay. So what we see here is a graph that would look like this. Alright, and so the red would be this function, f of x equals x squared plus 1. Now, if you looked at the two graphs, the shape is pretty much the same. Okay, so we notice that there's a difference, and the difference between the two is the fact that I added this plus 1. Alright, the fact that I added this plus 1 to the parent function, which is x squared, because we talked about it in the previous screen. I showed you that the graph of f of x equals x squared gives you a base u whose vertex or lowest point sits on the x-axis, alright, at 0, 0 at the origin. But now if you notice, if we add this 1 to that parent function, the same graph, the same profile exists. But what we ended up doing is we ended up shifting every point on our parent function up 1. Every point on our parent function got shifted up 1. Okay, so that's the definition of a vertical shift. Alright, so with a vertical shift, what you can expect to happen is that you have some constant. The way they write it would be like h of x equals your parent function. This would be your parent function plus some constant. Alright, and that would yield a vertical shift. Okay, vertical shift upwards. Now, still talking about vertical shift, if in contrast we had some function equal to our parent function minus some constant, then that would yield a vertical shift downward. So basically, if I had a situation where, let's say, you had f of x equal square root of x minus 2, something like that. Alright, well, I know that the graph of the square root of x, I showed you in the previous graph, if you had square root of x, it'll give you a profile that look like that, where its origin, it starts at 0, 0, which is the origin, where the two axes, the x and y axis, cross. Okay, well, the fact that I'm subtracting 2 from that base graph, subtracting a constant from a parent function, this being the parent function, this is the constant I'm subtracting. The fact that I do that tells me that I'm basically going to take the same graph and shift it vertically, but because it's a minus sign, instead of shifting it up, we're actually going to shift it down. So if this profile fits the square root of x, which is a parent function, at y is 0, then we would shift it down 1, down 2 units, and we'd write the same graph, but now it's 2 units lower. And that's what we mean by transformation. Alright, we took the same graph and we modified it some kind of way. We moved it, we reshaped it on the same shape, but we may have shrunk it or expanded it. But in this case, all we did was move the graph down 2 steps. Alright, so that's what we mean by a vertical shift. Okay, so to give you a better view, let's see, and this will be in just general terms. Alright, so if we're saying here, do even better, plug in a couple of points. Alright, so now we're going to say our f of x is equal to, let me erase these as well. So hopefully this illustrated better. Alright, you have f of x equals square root of x, which is a parent function, and then we said f of x equals the square root of x minus, square root of x minus 2. Okay, so a parent function minus a constant, So here we could write a 0. Alright, we could write positive 1, and then I want to write 4. Okay, and the reason why I picked those 3 numbers, one, they're all positive because we don't want to take the square root of a negative, and then they're all perfect squares, so I can get nice whole number answers. So square root of 0 is just going to be 0, square root of 1 is 1, square root of 4 being 2. Okay, so I have those. Now I take those same here. Alright, so square root of 0 is 0, but then minus 2 gives me a negative 2 when I plug in a 0. Plug in 1 for x. Square root of 1 would be 1. Alright, but 1 minus 2 is a negative 1. Alright, plug in a 4 for x. Square root of 4 is 2. 2 minus 2 would be 0. So first I'll plot these points. So there's my 0, 0, my 1, 1, 1, 2, 3, 4, 2. Alright, so my parent function, in essence, looks like this. Okay, so now I'll create my transformation. So I have my parent function minus 2, minus a constant. So at 0, I have negative 2. So at x is 0, y is negative 2. So that's right here now. At x is 1, y is negative 1, so x is 1, y is negative 1, and at x is 4, y is 0, so x is 1, 2, 3, 4, y is 0. So there's my function. And if you notice, because I have the minus 2 added on to my parent function, the minus 2 is tacked on to my parent function. All it means is I'm going to do a vertical shift of the parent function. So the black represents the parent function, and because it's minus 2, I just drop this parent function down 2 units. So that point gets dropped down 2 units, that point gets dropped down 2 units, that point gets dropped down 2 units. So all it does is end up relocating my parent function 2 units below its original location. Alright? So hopefully that helps you understand vertical shift. Okay? Now, in general, vertical shift takes place when you have a constant being added or subtracted outside of the function. Okay? It's being added onto the function, not into the function. Okay? So vertical shift is when you have some constant being added outside of the function, or subtracted outside of the function, for that matter. Alright? Okay. Okay, let's see here. Alright, so that's vertical shift. So now let's look at one like, let's see. Let's go with change my color back. Okay. So let's go with x to the third, which is one of our parent functions, versus x minus 1 to the third. Okay. So we'll make our table of values. -2, -1, 0, 1, 2. So at -2, y would be, what is that, 8, -8. Okay, -1, you get a 1, 0, 0, 1 you get a 1, and 2 you get a +8. Alright, so now we come over here, same numbers. So at -2, -2 minus 1 gives me a -3, and a -3 to the third gives me a negative, what is that? I want to see. -2 minus 1, so -3, -3 to the third, it's -27. Okay. -1 minus 1 gives me a -2, so a -2 to the third gives me my -8. Okay, then my 0 minus 1 is a -1, -1 to the third gives me a -1. 1 minus 1 gives me 0, 0 to the third, 0. 2 minus 1 is 1, 1 to the third is 1. And let's say if I put a 3 here, alright, 3 minus 1 is 2, 2 to the third, +8. Okay, so if I plot these points, I have my 0, 0. First plot my parent function, -1. Oops, there should have been a -1 still over here. Okay, so -1, -1 would be there, and -2 down 1, 2, 3, 4, 5, 6, 7, 8. Barely had enough space, but we worked it in. Alright, so -2, -8. There's my 0, 0. 1, 1. Then 2 up. 1, 2, 3, 4, 5. Excuse me. 1, 2, 3, 4, 5, 6, 7, 8. So what you end up with is something that looks like this. Alright, I know it's not the prettiest of graphs, but you get the point. Okay, so that would be drawing your parent function here. Okay, now if we plotted these, and I'll skip this point and I'll stick with these here. Alright, so my -1, -1, and I'll change color. -1, -8 goes here. 0, -1, 0, -1, 1, 0. Wait a minute. 0, -1. Uh-oh. That's wrong. Take that off. Can I erase that without erasing the line? Ah, dog it. Didn't mean to do that. Want it back in black. Okay. Come on now. Okay, there we go. Alright, so we're doing our line. Alright, so now go back to my points. I have the -1, 8, because I'm doing this function now. Alright, doing this function now. So I have my -1, -8, 0, -1, 1, 0, 2, 1, and then 3, 8. So that gives me a function that looks like this. Alright. So if you notice now, instead of me taking my parent graph and shifting it up or down, now the parent graph actually got shifted over. Alright. Got shifted over to the right 1 unit. Each point shifted over to the right 1 unit. Alright, and that's because of this -1 was embedded inside of my parent function, which is x to the third. It's inside of there because you see it inside of the parentheses. So the fact that it's embedded inside of the function tells me that I will now have what we call a, let's see it, alright, what we call a horizontal shift. Okay, and for horizontal shift we have where h of x equals a parent function where the constant is embedded, and if it's minus, we would typically think of minus, if in horizontal terms we would think of minus going to the left, but actually it would mean a shift to the right. And if you have a constant being added inside of your parent function, then that means you'd have a horizontal shift to the left. Okay, so I just showed you there how it shifted to the right, how the black parent function shifted to the right, you see in red, by 1 unit because we have this -1 that's embedded inside of the function. Alright, so let's look at, let's say, another function here. So let's erase. Okay. Alright. Erase, erase, erase. Okay, so now let's say we want our function to be absolute value of x. So once again, -2, -1, 0, 1, 2. So absolute, plug in a 2, absolute value of 2 is 2. Plug in a 1, 1, 0, 1, 2. Come over here. Now over here I want absolute value of x plus 1. Alright. And so let's see. Negative, if I say a -2, alright, so let's say a -3, -2, -1, 0, and a +1. Alright, so let's go with that. So when x is a -3, -3 plus 1 is a -2, and the absolute value of a -2 is a +2. Alright, plug in a -2, -2 plus 1 is a -1, absolute value of a -1, +1. -1 plus 1 is a 0, absolute value of 0, 0. Plug in a 0 for x, 0 plus 1 is 1, absolute value of 1 is 1. Plug in a 1 for x, 1 plus 1 is 2, absolute value of 2 is 2. So I have those points. So I'll graph my parent function first, my 0, 0, as always. Alright, -1, 1, +1, 1, -2, 2, +2, 2. So what we have is a parent function that looks like that. There's my parent function. Okay, so now we notice this +1 is inside of the absolute value. So it's inside of the function. So that tells me it's going to be a horizontal shift. Okay, inside. Here, to give you an idea, this is inside. Outside would be if it looked like this. Now this is happening outside of the absolute value. That's outside of the function. That's outside of our parent function, and this will cause for a vertical shift. But the fact that the +1, the constant, is inside of the function, that's the reason why it's a horizontal shift. So I plot these points. Okay, so I have a -3, 2, 1, 2, 3, 2, -2, 1, -1, 0, 0, 1, and 1, 2. So now you see you have this and that. And just like we said, there is a horizontal shift. And the +1 is inside. And +1, again, is opposite of what we would typically think when we're talking horizontal. Typically when we're talking horizontal plus, we usually want to count right. But according to our little formula here, we would actually shift to the left. And if you notice, our black graph is our parent graph, and the red is 1 unit shift to the left. Every point from the black has been shifted 1 unit to the left in red. Okay, so those are your shifts, vertical and horizontal shift. Alright, so now let's shift our focus to play on the pun, shift. Okay, and we can talk about reflections now. Okay, reflections. Alright, and let's erase these, erase these, erase these. Okay. I knew that was going to happen. Okay. Let's see. Alright. So now we're going to go to a parent graph, and we have square root of x. Okay, and so square root of x, 0, 1, and 4. I like those points. Okay, and now what I want to do is I want to throw the negative outside of the function, outside of the square root of x. Okay, and I'm going to stick with 0, 1, and 4. Alright, so now for my parent function, 0, square root of 0 is 0, plug in a 1, square root of 1 is 1, plug in a 4, square root of 4 is 2. Alright, for my second function, plug in 0, still get 0, plug in a 1, square root of 1 is 1, but now a negative gets attached to it, so I get a negative 1. Plug in a 4, square root of 4 is, square root of 4 is 2, attach a negative to it. Okay, so let's graph them. 0, 0 I have, 1, 1, 1, 2, 3, 4, 2. Alright, so you have that there. Okay, and then we plot our second function, 0, 0, so it's also here. Alright, 1, negative 1 is here, and 4, negative 2 is here. So this one looks like that. Okay, and so what you see here is what we call reflection. Alright, reflection. Okay, reflection, and in this case a reflection about the x-axis. Alright, so in other words, what happens is it looks like you take the parent graph and you just rotate it around the x-axis. Alright, it just looks like it swings around the x-axis. So a mirror image of itself on the x-axis. Okay, that's what we mean by reflection. And so anytime the negative sign is outside of the function, your reflection will be about the x-axis. Well, okay, well let's look at what would happen if it's inside. So create a third function for us where the negative is now inside the function. It's inside the square root of x. Alright, we make our little data table. And so here, your 0, negative 1, negative 4. Okay? So when x is 0, 0, negative 0 is still 0. Now notice I made these numbers negative. Why? Because a negative times a negative makes it positive. And I need the answer or the value under this square root to be positive because you can't take the square root of a negative. Alright, so I make this positive. So this negative 1 times a negative sign, negative times a negative 1 makes it a positive 1. Square root of positive 1 is 1. This negative 4 times the negative that you see right here. So this negative times whatever x is, and x is a negative 4. So that negative times that negative makes it a positive 4. And the square root of a positive 4 is 2. Alright, so now you have your 0, 0, negative 1, 1, negative 1, 2, 3, 4, 2. Oops, that didn't look good. Okay, so now there you have it. And that's the behavior you get when the negative sign is inside the function. When the negative is inside the function versus outside. That's outside the function. This is inside the function. When it's inside the function, the reflection of the parent graph is now around the y-axis. Alright? So, when the negative is inside the function, your parent function basically just spins around the y-axis. If your negative is outside of the function, then your parent graph spins around the x-axis. Okay? So there's reflection. Okay? Alright, let's erase. Didn't mean to erase all of that, but oh well. We'll deal with it. Okay. Alright. Let me come back here. Make lines. Alright. Alright, so I have our graph again. Okay. So now, what happens if we have something like excuse me. Our parent function, secondary function. Alright, so parent function, -2, -1, 0, 1, 2. Alright, so -2 squared is going to be our 4, our 1, our 0, our 1, and our 4. Alright, and then over here, if you have a -2 squared, alright, that gives you 4, but now it's being multiplied by 2. Okay, so you end up with, what is that, 8. When you plug into -1 squared is 1. Alright, but that's going to give you a 2 because it's times 2. 0 still give you 0. Positive 1 give you a 2. And a positive 2 gives you an 8. Alright, so now let's look at plotting these. Okay, so first, there's our 0, 0. Alright. -1, 1. 1, 1. -2, 4. Positive 2, 4. And there you have it. Once again, your parent function. We already knew this. Alright, but now, notice I'm multiplying a constant outside of my function. So my function is my parent function is getting multiplied by a constant. Okay? And when that happens, let's notice the effect. At -2, we're up 1, 2, 3, 4, 5, 6, 7, 8. Well, here, let me change color. Alright, at -1, we're up 2. 0, 0 is shared. Alright, at 1, we're up 2. and at 2 we're up 8. So now the graph looks like that. Okay. Alright, so the fact that we've multiplied our graph, our parent function, okay, by a constant that's greater than 1. Okay, this 2 is greater than 1. So anytime the constant is greater than 1, if the constant is greater than 1, then you have what you call a vertical stretch now. Alright, so it would be like if we grabbed the parent function in black and we pulled up from the ends. If we grabbed it at the ends and pulled up, if we grabbed it at the ends and pulled up, it would tighten like you see here. It would get skinnier and it would stretch upward. Alright, it would get skinnier and stretch upward. Alright, so that's why it's called a vertical stretch. Okay, if let's say instead of 2 that were 1/2 x squared, so now your constant that's being multiplied by your parent function is now, between 0 and 1. Okay, so now your constant is greater than 0, can't be 0, but it's less than 1. Alright, so now you're talking a fraction, less than 1. That's what we call a vertical shrink. And in that case, what would happen is, okay, let's say we had the same points. Alright, -2, -1, 0, 1, 2. Alright, and we're saying now f of x equals 1/2 x squared. Okay, x and f of x. Alright, so now at -2 squared is 4. Half of 4 would be 2. 1, -1 squared is still 1. Half of 1 is 1/2. 0, positive 1 would be 1/2, and at 2 you get 2. Okay, so if you apply to these points, what you'd notice, you still have your 0, 0 in the middle. At positive 1 you get 1/2, and at -1 you get 1/2. At positive 2 you would get 2, and at -2 you would get 2. Alright, so you see it's called a vertical shrink when your constant that's multiplied by your parent function is less than 1 but greater than 0. In other words, is a fraction. Okay, is a fraction. It's a vertical shrink, and you see it right here. If our parent function is in black, you see how it gets wider at the base and it's pulled out. So it'd be like having your parent function pulled out, which causes it to get wider at the base and not to reach quite as high. Okay, so it doesn't reach quite as high as your parent function would. Thus, your vertical shrink. Okay, so that pretty much covers our transformations. If there are any questions, as always, feel free to contact me. But at this time, we will go ahead and conclude this session.